Welcome back. It's now time to complete some static studies on a power system network model for our new Sunny Solar Farm. The site can support at most a solar farm of 97 megawatts AC. In this video, we will start with the power system modeling to answer one question. Can the local network infrastructure support such a large generator? The first step in the process is to request a power system model of the local electricity network from the company which owns and operates that network. In Australia, such a company is called a network service provider, or NSP. Since we are connecting at 66 kV in Victoria, and the NSP in our area of the solar farm is called United Energy. Now, really important to highlight right now, all the network data which I'm about to show has been made up. It is not reflective of the actual network assets. We've tried to tie this tutorial as close as possible to a real-world grid connection process so it will align with your work or your projects. The locations are real, the electricity network is real, but the data isn't. The 66 kV line to the north of our solar farm is the Tyabb Terminal Station, TBTS, to Dramana, DMA, 66 kV line. Our solar farm is about 12 kilometers from TBTS and the total line length is 29 kilometers. So let's pretend that I requested a PSSE network model from the NSP and receive what is on screen right now. So our reminder, our objective for this investigation, check that by adding our new solar farm, are we causing any assets to be overloaded that weren't overloaded before we put the solar farm in. A quick intro on the model we're looking at. On the left-hand side, we can see the 220 kV transmission network which supplies this sub-transmission area. On the right-hand side in green are all the 66 kV assets that make up the 66 kV network we are investigating. Each bus has two lumped loads which represent all the distribution connected loads on those substations. Now, let's ignore the difference between MVA and megawatts for now and just look at raw numbers. The first thing we notice is the Tyabb Dramana line that we are connected into has a maximum line rating of 75 MVA, and that's lower than our intended maximum output power of 97 megawatts. Let's start with Sunny Solar Farm out of service and look at the network as is under high load. Under high load with system normal meaning everything in service, each line is loaded less than 60%. If we simulate a contingency, known as a system N-1 condition or one line out of service, if we disconnect the most heavily loaded line, which is one of the Tyabb to Mornington lines, we can see the remaining second line hits 98% of its thermal capacity. Yet again, without our solar farm in service, let's check what happens if there's an outage of the Tyabb Terminal Station to Dramana line, the line our solar farm connects to. We can see that under high loading, the DMA bus load is supported by a single line via Mornington. It is pretty heavily loaded, but it doesn't breach any thermal limits. Let's put Sunny Solar Farm in as a new lump generator at the Sunny Solar Farm POC bus. We'll set the generator's maximum power to 97 megawatts, that's from the last video, and we'll set its minimum and reactive power to 39.5% of 97 megawatts. We'll see why in a future video. The network model is currently configured for maximum summer demand, which in Australia typically occurs at sunset. Now, at sunset, a solar farm won't be exporting so much power, but we'll test it anyway. With Sunny Solar Farm in service, we can see higher loading on the lines than the previous test when it was out of service, especially the Tyabb to Sunny Solar Farm line, but no line thermal limits seem to be exceeded, so it's looking good so far. Now let's repeat the same N-1 contingency as previously. What happens if there's an unexpected outage of one of the Tyabb to Mornington lines? We can actually see our solar farm is helping in this case. It helps reduce network loading as power is flowing from the solar farm through Dramana to Mornington. But if we look back at the single line diagram once we added our solar farm, the most heavily loaded line is not Tyabb to Mornington anymore. It's Tyabb to Sunny Solar Farm. So what happens if that line goes off suddenly? Yeah, we can see some pretty serious overloads happening. Both Sunny Solar Farm to Dramana and Dramana to Mornington are greatly exceeding their thermal limits. This is a problem, as before we put the solar farm in, we didn't exceed thermal limits. So the project has a choice. Option 1, make the solar farm smaller. Option 2, implement and pay for a special control scheme which detects any outage of the line of section from Tyabb, Sunny Solar Farm to Dramana, Dramana to Mornington, and automatically reduces power on the solar farm below a preset threshold. This special protection scheme is called a runback scheme. Runback schemes can be pretty expensive, but in the interest of this example, let's proceed, assuming our project is happy to provide the extra cost for the scheme. So if there was a runback scheme, the safest option is to run back to zero active power, but continue to provide reactive power support. This limits the chance our generator will overload any lines under any other scenario. So let's just check what would happen. Tie-ab to Sunny Solar Farm is out of service, and our solar farm is doing 0 megawatts. And those two lines are no longer overloaded, meaning our runback scheme plan worked. One more thing we need to check is low demand. If you switch all the loads in the network to low demand and put the solar farm at maximum power, which is possible, low demand could be a very sunny day with lots of embedded generation, we can see the tie-ab to Sunny Solar Farm line is overloaded. This is a system normal overload. This is a clear indication that our generator is just too big for the network. Yet again, we have two options. Option 1 is pay to upgrade the 12-kilometer line segment between tie-ab and Sunny Solar Farm so it can carry additional power, or reduce our solar farm size. Reconductoring line is very expensive, so let's opt to reduce our solar farm size slightly. We can see if we reduce from 97 megawatts to 72 megawatts and adjust our reactive power capability by the same factor, the line loading drops to an acceptable level. So what have we identified from this investigation? Firstly, a 97 megawatt solar farm is too big for the network because it causes a system normal overload on the tie-ab to Sunny Solar Farm 66 kV line. Reducing the solar farm to 72 megawatts removes the system normal overload and a minimum expected loading. If there is an unplanned outage of any line between tie-ab to Sunny Solar Farm to Dramana to Mornington, the solar farm could overload a remote line segment. The solar farm has to have a special protection scheme to automatically run back the generator to 0 megawatts active power if such outage is detected. So now we know. Our generator Pmax is 72 megawatts.